A 3.3 billion light-year arc just turned up. It should not be there at all. Here is the immediate takeaway in simple words. The universe should look uniform when you zoom out enough. That arc looks coordinated far beyond that supposed smoothing scale. Uniform means big patterns blur away at truly giant distances. The arc refuses to blur, and that is the shock. Astronomers mapped distant gas using quasar light and saw the curve. They did not stack pretty images, they traced absorption fingerprints. A basic rule got a hard stress test and squeaked. Quick mental image, a faint silver bow laid across deep night. I am not saying physics is broken overnight. I am saying we found a bold outlier that demands checks. We will tour the biggest claimed structures and the arguments. You will see how statistics and sky maps can disagree. Bottom line, one arc lit a fuse under cosmic sameness. Stand on a dark plateau under a sky packed with galaxies. Cosmologists lean on the cosmological principle, a simple guiding idea. It says the universe looks the same at large enough scales. That matters because our equations assume no special places or directions. If the average shifts with location, predictions wobble and drift. So what is large enough in plain words? The homogeneity scale is the size where counts finally stabilize. Think of tiling space with enormous cubes, then counting galaxies inside. At small cubes, counts bounce wildly because structures dominate each box. As cubes grow, fluctuations shrink and the average steadies. Zoom far enough and local lumps should cancel into smoothness. Inflation smoothed the early universe, then gravity grew later clumps. Filaments, walls, and voids emerged from tiny initial ripples. Simulations show this web, and observations broadly match that picture. Tiny tests double the cube size and watch variance drop. Observers estimate stabilization near a few hundred megaparsecs. That equals around 1 billion light-years, give or take. The giant arc seems several times longer than that benchmark. So the picture is, sameness sets our yardstick for cosmic claims. Now ride along a filament, a glowing highway through intergalactic darkness. Matter flows toward intersections, where galaxy clusters pile into knots. Those knots link into sinuous walls, leaving yawning voids between them. This quilt is called the cosmic web, a vast three-dimensional lattice. A great wall is not solid, it is a linked overdense ridge. We define structure by a linking rule that groups neighbors. Looser rules merge features, while stricter rules split them apart. That choice can inflate a feature or deflate it immediately. The GRB Great Wall was an early dramatic example. Later, the Sloan Great Wall looked even longer in survey maps. People cared because those walls grazed the homogeneity scale. Survey teams measured redshifts, then reconstructed a volume from slices. Software stitched galaxy positions into a continuous panorama of depth. You could trace connected chains across nearly 1 billion light-years, yet big simulations sometimes birth walls of similar apparent size. The catch is, definitions can assemble poems from scattered lines. Example in real terms, tweak thresholds and clusters suddenly percolate. Net result, claimed lengths depend strongly on how you draw boundaries. Picture an ultradistant quasar, a lighthouse punching through billions of years. Gas clouds in front leave fingerprints, small dips in the spectrum. Those dips tag magnesium-2, which traces normal galaxies along sightlines. Link many dips across the sky and you can track structure. That linked chain is the giant arc, announced in 2021. It spans about 3.3 billion light-years end-to-end. People care because it seems to exceed the homogeneity scale. The team mined archival quasar spectra and cataloged the absorbers carefully. Then they searched for coherent patterns across positions and redshifts. They reported a low false alarm chance after multiple statistical tests. Example in practical terms, a gentle tilt can look like a curve. Human vision loves arcs and the sky is full of points. Independent tests must repeat the method with similar sightlines and cuts. Replication is hard because quasar distributions are patchy on the sky. A second catalog is coming with cleaner calibrations and coverage. One sentence recap, evidence exists, but confidence still hangs on replication. Shift your view to a grand circle sketched across darkness. Another pattern appeared nearby in 2023, the Big Ring. A ring here means many tracers at one preferred distance. Arrange them around a center, and you infer a ring-like overdensity. That matters because preferred scales can hint at early universe ripples. Analysts again used magnesium absorbers seen in background quasar spectra. They found a clustering bump at a certain comoving distance. Fitting a circle on the sky, they reported coherence across angles. Real galaxies likely sit near those positions, anchoring the inference. But the ring is statistical, not a bright hoop you photograph. For scale, the diameter was about 1.3 billion light-years. Critics flagged projection tricks where arcs masquerade as circles in maps. Selection effects can also cherry-pick angles that enhance symmetry. Common mistake is forgetting how sky curvature warps apparent shapes. Follow-up work is testing robustness under stricter, pre-registered choices. Bottom line, the big ring is provocative and still under scrutiny. Sweep across a map of gamma-ray bursts, brief flashes from cataclysmic deaths. A bold claim surfaced of a vast wall, using burst positions. The Hercules Corona Borealis Great Wall stretched across huge sky angles. Here, a great wall meant many bursts at similar redshift ranges. People cared because the implied length spanned several billion light-years. That scale seemed to stomp the homogeneity expectation very hard. However, gamma-ray satellites never watch the sky uniformly at all. Exposure patterns vary, and detector backgrounds shift with orbital conditions. Detection thresholds change, and pipeline updates alter sensitivity over years. Distance estimates for bursts carry large uncertainties and selection biases. Put these together, and clumps can appear from uneven sampling alone. Example in plain terms, bright dots pile where you stared longest. Several follow-up studies reweighted data and simulated uneven exposures. Under those tests, the wall's significance weakened, sometimes dramatically. Net result, many experts remain unconvinced about that particular wall. Walk into a statistics lab where randomness makes convincing mirages. When scientists say something should not exist, they mean improbable. Improbable under what exactly, and compared to which rulebook? Under the probability rules of our best-fit cosmological model. That matters because rare events still pop up in wide searches. The sky allows many ways to slice, group, and link points. Every extra choice raises the odds of finding a striking pattern. This creeping freedom is the look elsewhere effect, a quiet trap. Rule of thumb, decide the recipe before you peek at results. Mechanically, you simulate many mock universes with the same average clumpiness. You apply the identical search, including thresholds and linking lengths. Then you count how often a structure that large appears. If that rate is not tiny, the claim loses bite. Example with numbers, 1 in 1,000 sounds rare to you, but search 10,000 recipes and you will likely see it. Pre-registration and blind analyses protect us from elegant self-deception. What to remember, significance lives or dies on repeatable tests. Focus on what our standard model actually predicts at giant scales. Lambda-CDM means dark energy with cold dark matter shaping structure. Quantum jitters in the early universe seeded tiny density wiggles. Gravity amplified those wiggles while cosmic expansion stretched their spacing. The two-point correlation function measures excess clustering over random placement. It shows a bump, the baryon acoustic oscillation scale, a preference. That scale today sits near 500 million light-years across. Preference does not mean a rigid ring stamped across everything. You still expect chance walls, arcs, and voids to show up. Their sizes follow probabilities, not strict upper limits like speed. Simulations the size of the entire observable patch remain impossible, but enormous ensembles already yield record-looking features occasionally. Example in practical terms, galaxy surveys show voids hundreds of millions wide. Those exist comfortably inside what Lambda-CDM expects from statistics. So the takeaway is, large alone does not mean impossible here. Peer into the near future, where new surveys sharpen the picture. DAISY is clocking millions of galaxy redshifts with exquisite precision. Euclid is mapping weak lensing and clustering across vast distances. Rubin Observatory will sweep the sky nightly, building deep time-lapse maps. SCA will trace hydrogen over cosmic time, unlocking three-dimensional structure. These projects matter because replication needs volume, depth, and uniform selection. Better calibrations reduce artifacts that masquerade as grand alignments. Mechanically, uniform selection keeps exposure and detection biases under control. Cross-correlating independent tracers checks whether patterns persist across methods. Example in real terms, a ring seen in absorbers should echo in galaxies. If an arc appears, lensing shear should hint at the same ridge. Data releases will allow strict pre-registered searches, avoiding hindsight tuning. Overlay that with transparent code and shared mocks for significance. Bottom line, the next wave will either solidify giants or quietly dissolve them. Step back to that shocking arc curving through deep time. It poked our sameness rule and forced careful rechecking of methods. Replication will decide whether it joins the canon or fades. Either way, the tests make our models sturdier and sharper. I love that science can say maybe, then go verify. If sameness holds, we learned our biases better with proof. If it bends, we get new physics to chase and tame. Thanks for exploring these cosmic giants with me tonight. If this scratched your curiosity itch, subscribe for more calm space dives.